Welcome back to the Deep Dive, where we turn groundbreaking research into immediate, actionable insight. Today, we are really focusing on those razor-thin margins of elite athletic performance. We're diving into what happens when a world-class swimmer is forced to confront one of nature's biggest variables, a moving river.
It's such a perfect scenario for a deep dive because the data we're looking at, it just strips away all the heroic narrative.
Yeah.
And it gives us the hard science on the limits of human adaptation. We're exploring the biomechanics of a champion preparing for the 2024 Paris Paralympic Triathlon, a really unpredictable course.
Swimming in the Seine River.
Exactly.
And the research behind this is captured in the paper. Stroke rate and arm coordination management in swimming in a double Paralympic triathlete champion.
A really meticulously detailed study. It was published by Ludovic Seifert and his collaborators. You can find it in the Journal of Sports Science and Medicine. That's volume 25, pages 211 to 220, published online in March 2026.
So our mission for you is to understand exactly how this elite para-triathlete has to adapt his technique to cope with that intense current. And what are the hidden, scientifically measurable costs of that adaptation? It's really a shortcut to understanding efficiency right at the human limit.
And that river current is a serious opponent. I mean, the course requires athletes to swim both upstream and downstream on the Seine. Estimates for the flow rate were hovering around, what, 0.5 meters per second?
Wow.
Think about that. You're fighting the equivalent of a treadmill running against you for half the race. That demands immediate and very high cost biomechanical changes.
Okay, let's unpack this. Before we can even talk about adaptation, we have to establish the language of swimming efficiency. It's so much more complex than just fast or slow. We need our foundational metrics.
Absolutely. The first layer is the simple one. Swimming speed, let's call it S, is a function of two things. Stroke length, or SL, how far you move forward in one arm cycle, and stroke rate, SR, which is how many cycles you do per minute.
So speed is just the product of those two.
Exactly. You can swim fast by taking long strokes slowly or, short strokes quickly or some combination.
Right.
But the real secret ingredient, the thing that determines how efficient those strokes are, is the index of coordination, or IDC.
Okay, tell us about the IDC, because this is where we really start to visualize the technique.
So the IDC quantifies the timing, the temporal relationship, between the propulsive phases of the two arms. It basically dictates your whole swimming style.
Yeah.
Most elite swimmers fall into one of two categories. The first is catch-up, where the IDC is negative.
Okay.
Think of this as hand-in-the-pocket swimming. One hand enters the water and completes this long glide phase before the other hand even starts pulling. It emphasizes length, minimizing drag, and it's the hallmark of long-distance specialists, triathletes.
A relaxed, sort of energy-saving style built for the long haul.
Precisely. And then you have superposition, where the IDC is positive. This is continuous propulsive action, which you might call windmill thrashing.
Oh.
Yeah, there's no glide time. One hand is entering the water and immediately starting its pull before the other has even finished. This is your sprinters. They prioritize maximal force over saving energy.
And previous research gives us a strong clue about what the Seine would demand, right? When you're swimming with a current, you want to minimize drag, so you maximize that glide. You use the catch-up pattern.
That's the theory. But when you're swimming against a current, you are effectively creating this artificial drag. So to maintain your speed, you have to overcome that drag by increasing force and tempo. You have to shift toward a higher stroke rate, shorten that precious glide time, and that pushes you toward that less efficient superposition pattern.
And the study focuses on a fascinating subject. An elite male para-triathlete, PTS4 class. He has a moderate physical impairment, specifically a right lower leg amputation, and he's already a multi-time world and Paralympic champion. Why is his unique physical challenge so important to this data?
Well, it adds a layer of complexity. The amputation changes his body's natural buoyancy and balance. It makes the integration of his arms and torso even more critical to stabilizing his stroke length. So his ability to adapt under stress, which is what we're about to measure, isn't just about technique. It's about compensating for an inherent physical asymmetry.
So we have two main tests to analyze his motor organization and really to understand his physical limits. They didn't just look at his race performance. They built this incredible scientific picture of his body's factory settings.
Right. Test 1 was the incremental test. It was designed to map his SSR relationship, the speed-to-rate curve, to find his maximum efficiency point. He did 10 reps of 25 meters, self-selecting speeds from his slowest comfortable pace right up to maximal effort. a 40% speed increase overall.
And the goal there was to model that relationship to identify two crucial things: his natural modes of functioning and the exact stroke rate where his stroke index was maximized. And the stroke index, that's SI, right? That's the combined measure of speed and length, the gold standard for efficiency.
That's the one. And that model revealed two crystal clear regimes. Regime 1 showed stable efficiency, his comfort zone. Regime 2 showed biomechanical breakdown, the point of no return. The science here is it's so impressive because it gives us an objective transition point, not just a subjective feeling of, getting tired.
Okay, so once they had a stable zone, they moved to test 2. This was all about energy constraints and adaptability. This is where they brought in the auditory metronome, the tempo trainer.
Yes, that's the crucial element. For the second test, he swam 6 reps of 50 meters, all aiming for a consistent pace, 1.41 meters, which matched his personal best for the 800-meter event. But they used that tempo trainer to impose 6 different stroke rates: his spontaneous rate, and then modulations of -3, -6, +3, and +6 cycles per minute. They forced him to swim either slower or faster than his body wanted to.
That must feel incredibly restrictive, having a beep telling you exactly when to complete your cycle. So what were the key measurements they took to quantify the cost of those forced paces?
They needed to quantify the metabolic and mechanical penalty of being pushed outside his comfort zone. So they measured total energy expenditure, or E-total, that's the total caloric cost. They computed this by measuring post-exercise oxygen uptake for the aerobic component and blood lactate for the anaerobic cost.
So measuring exactly how much fuel he was burning per 50 meters.
Precisely. And the second crucial measure, which is maybe the most unique takeaway from this research, was the jerk cost.
Jerk cost. Okay, you have to break that one down for us. What does that actually mean? Is it like a jerky motion?
That is a perfect way to think about it. It's a
Okay.
measure of stroke smoothness. A lower jerk cost means smooth, fluid mechanics, low wasted effort. A high jerk cost means a jerky, inefficient stroke. Your body is fighting itself.
So let's get to the results from test 1. What's fascinating here is how clearly the athlete prioritized that glide when he wasn't being stressed.
In that low pace, regime 1, he was absolutely maximizing his efficiency. He maintained this astonishingly high and constant stroke index Cymax was 3.16 meters squared per second. And his coordination pattern was a deep catch-up, with an IDC between -13% and -10%.
Wow.
This reflects a prolonged upper limb glide, just maximizing efficiency, minimizing active drag. The study even compared this to the burst and coast swimming behavior you see in certain fish, like cod. It's a fundamental strategy for energy preservation.
That makes perfect sense. The longer you glide, the less you have to fight the water. The transition point where he switched from that comfortable glide mode to the high force mode, that happened at 1.28 meters per second and a stroke rate of 31.1 cycles per minute. Is that the speed where his body essentially hit a metabolic wall?
That's exactly where the efficiency started to drop off, significantly. Once he hit regime 2, his efficiency immediately started to decline. As his SR increased toward maximal speed, all the way up to 61.3 cycles per minute, the proportional increase in his swimming speed just lagged way behind. His stroke index decreased by a staggering 74%.
74%. I mean, to put that in perspective for you, that's like putting in 4 times the effort to get maybe a 5 or 10% marginal increase in speed. That is a massive, unsustainable energy penalty.
And this leads us to the key metric for his coaches and for our deep dive. The point where he started dropping from that optimal efficiency model was precisely 44 cycles per minute.
44. And that rate, that corresponds exactly to his preferred SR he uses in competition, the 800-meter race. So the data confirms 44 cycles per minute is his absolute peak efficiency before significant biomechanical compromise sets in.
Any faster, and he starts sacrificing the glide and the smoothness that his body relies on, especially given the stabilization requirements from his PTS-4 classification.
Okay, so now we move to test 2, which is where it gets really analytical. The researchers knew his optimal rate was 44, but they forced him out of it to see the energetic fallout.
Yes, and the first surprise was that his spontaneous rate in the test was already 50 cycles per minute, which is already higher than his measured efficient rate of 44. It suggests that even under non-competitive pressure, he naturally tends to push the rate a bit too high.
And when they imposed the higher rates, 53 and 56 cycles per minute, the athlete struggled. This is the moment the science confirms the hypothesis. Swimming faster than your optimal SR comes with a massive cost.
That's exactly what the numbers show. When they compared all the imposed rates, the condition at SRS-6, which is 44 cycles per minute, it unequivocally confirmed its status as the optimal point. This condition achieved the highest stroke index and the lowest total energy expenditure at 93.65 kilojoules.
It was his metabolic sweet spot, and crucially, it was also the smoothest stroke.
Absolutely. The 44 cycles per minute condition resulted in the lowest jerk cost. Conversely, when they pushed him to the highest rates, 53 and 56 cycles per minute, those conditions were really hard for him to sustain. And they resulted in the highest E-total, up to 109.64 kilojoules. And that increased energy demand wasn't even translating into proportional speed.
I think we need to make that connection between jerk cost and E-total really clear here. Let's use an analogy. If the jerk cost is the measure of the stroke's smoothness, like the vibration in your car's steering wheel, then E-total is the measure of your wasted fuel.
That's a perfect analogy. If your steering wheel is vibrating violently, high jerk cost, your engine is unhappy. And you are wasting fuel to friction and inefficiency, which is higher total. The athlete was wasting energy because he was thrashing, not gliding. The data confirmed this with strong statistical correlations. Higher E-total was directly linked to a higher IDC shifting toward that thrashing pattern, and significantly linked to higher jerk cost.
So, pushing the tempo immediately compromises biomechanical smoothness, and the body's metabolic engine pays the price. He was sacrificing efficiency for speed that wasn't even materializing effectively.
And if we connect this all back to the bigger picture, the Paris Triathlon on the same, the study confirms that for this elite para-triathlete, maximizing efficiency relies heavily on operating around that preferred SR of 44 cycles per minute.
So what does this all mean for actually swimming in those variable river currents? This is the application we need.
It dictates his race strategy. I mean, when he's swimming with the current going downstream, his natural low-pace, high-glide catch-up pattern is highly functional. The current assists him. It lets him operate in his high-efficiency regime 1.
But the challenge comes when he turns around to swim against that 0.5 meter per second current. He has to increase his stroke rate significantly to maintain a competitive speed against that drag.
And that's where the efficiency limit is exposed. When he's forced to increase his SR much above, say, 44 to 50 cycles per minute, he quickly crosses into that inefficient regime 2. He incurs higher total energy expenditure, higher jerk cost. His range of adaptable speed is functionally limited by the onset of this biomechanical breakdown.
Which provides very clear, very specific training advice. It's not just about hitting the 44 cycles per minute target, but training the flexibility around it. So he doesn't immediately jump to that jerky, high-cost pattern the moment he needs to speed up.
Exactly. The recommendation for his coaches is to deliberately modulate SR conditions in training. The athlete needs to learn how to functionally adapt his arm coordination, specifically maintaining the quality and duration of the catch and glide phase, even when the metronome demands a faster tempo.
Yeah.
He needs to stretch the efficiency of his preferred rate to cope with that intense upstream demand.
It's a remarkable illustration of how the science of movement can quantify the hidden costs of athletic adaptation. The main finding is a scientific goldmine. Efficiency is tightly coupled to a preferred stroke rate range, and pushing beyond it incurs a measurable energetic cost that is perfectly mirrored by the degradation of stroke smoothness, the jerk cost.
And that strong correlation between jerk cost and total energy expenditure is something that previous experimental studies hadn't really explicitly confirmed. It raises an important question for future researchers. In complex motor skills, is smoothness itself the primary predictor of energy efficiency? Or is that measurable mechanical smoothness merely a consistent consequence of the most metabolically sound movement pattern? Something for you to mull over.
A fascinating dilemma. We strongly encourage you to read the full article by Seifert and his colleagues. Its detailed methodology and figures really visualize those two functional regimes and the SSR curve. Thank you for diving deep into the science of performance with us.
Follow our channel and turn on notifications for more deep dives into the science of performance and human limits. We'll get you next time.